Assalamualaikum. My name is Mahfuz Zuhdi bin Masnan and my partner is Mizal Haireez bin Faizal. Today we will present our computer-aided production management mini project on parallel processing and assembly station simulation. We extended lab scenario 3 by adding part D and analyzing system performance through theoretical calculation and cross simulation. In next 10 minutes, we will cover our system design, theoretical analysis, simulation result, and improvement recommendation. Next, I will pass to my partner, Mizal.
Okay, so we're gonna start it with the lab scenario, which is basic parallel processing system with parts A and B. Our extension, our extension added part D with 120-second inter-arrival time and new machine D1 with 95-second processing time. We assign ops 5 as the dedicated operator for machine D1. The key change was modifying the assembly process. Instead of 1A plus 1B equal to 1C, and now we have now have 1A plus 1B plus 1D equal to one product of C. So Mahfuz, can you display the full layout of simulation? Okay. So here you can see our layout with three sources for machines, multiple buffers, and five operators. Part A arrive every 90 seconds, part B every 100 seconds, and part D every 120 seconds. Assembly time is 150 seconds constant with 50 seconds load and unload. The system operates 9 hours with standard break schedule and machine breakdown parameters. And then for the theoretical analysis, okay, we use standard industrial engineering formulas. We calculated cycle times, including processing, load and unload, and setup times. Basically, machine A1 is a 95 seconds total cycle time, machine B1 100 seconds total cycle time, machine B1 120 seconds total time, and then the last part assembly station 170 seconds total cycle time. So to show the table for the production rate analysis, we can see that machine A1 is 40 parts per hour. Machine B1 37.9 parts per hour. Machine D1 34.3 parts per hour, and the last one assembly 21.8 per hour. And then converting cycle times to hourly production rates reveals system capacity. And then assembly station clearly emerged as the bottleneck with lowest rate at 21.2 parts per hour. This means regardless of upstream machine performance, system output is limited to assembly capacity. So for the theoretical prediction, based on bottleneck analysis and accounting for break times, we predicted 169 product C units in 8 effective working hours. This calculation assumes perfect material flow and no additional constraints. However, as we'll see, simulation reveal a different reality. For the simulation result overview, our simulation produced 110 product units, which is 83% higher than our theoretical prediction of 169 units. This represents an average production rate of 34.44 parts per hour from the assembly station. And then the system processed over 4,500 total parts during the 9-hour simulation. Um, so the key performance metrics, I want to highlight the assembly station operated at 81.58% utilization, confirming its bottleneck status. System experienced 35 machine breakdowns across all equipment, yet still exceeded theoretical performance. So individual machines showed much higher utilization than expected. However, we discovered some critical inefficiencies that need addressing. So that's all from me. I move to Mahfuz.
Okay, next, I'll talk about the critical analysis and findings. Performance comparison charts. Every single machine exceed theoretical calculation by substantial margins. Machine B1 showed most most dramatic Machine B1 showed most dramatic improvement at 336% above theory. Even our bottleneck assembly station performed 58% better than calculated. This suggests our theoretical model were conservative and didn't account for operational efficiencies. Bottleneck performation. Despite higher performance, assembly station remained the system constraint. In 34.44 parts per hour rate still limited overall system throughput. This confirm our theoretical bottleneck analysis was correct, even though specific number is different. For the critical efficiency discovery, we discovered a shocking efficiency of OPS3 operated at only 2.41% utilization. Okay, here is the utilization rate for the OPS3. This operator was responsible for transporting part to assembly, but was severely underused. The position of the OPS3 is at here, at the buffer before the assembly machine. Despite traveling 938,000 millimeter during the shift, OPS3 handled only 166 part versus 310 product assembled. So for the problem identification and root cause. Firstly, we view for the labor misallocation analysis. OPS3 is extreme underutilization, represent wasted human resource and poor job design. While other operator, OPS1 at 83.72%, OPS2 at 82.24% were optimally utilized. OPS3 was essentially idle. This suggests either inappropriate test assignment or fundamental process design flaw. Next is for the flow imbalance evidence. Massive part accumulation upstream of assembly proved poor synchronization. Thousands of parts were waiting while assembly struggled to keep pace. This tied up working capital and indicates inefficient material flow design. So at the buffer A2, it can only show only 909 part here. And at the B2, only is 1,431 part, and at buffer D2 is 972 part. And at the assembly buffer is only 10 part. So this prove the poor synchronization in the system. So next is the work in process inventory problem at the simulation 8. At the simulation N, 953 part A. Show the part first. Okay. At the simulation N, 953 part A, 1,460 part B, and 989 part D remain in the system. This represents significant work in process inventory that doesn't contribute to output. Poor part synchronization means we are producing parts faster than we can assemble them. So for the improvement and recommendation, we can make an immediate action by we assign OPS3 to directly support assembly operation or cross-train for multiple function. Next is to implement buffer monitoring system to prevent excessive accumulation. For the next one is to establish preventive maintenance program to reduce the 35 breakdown we experience. Next is strategic improvement. We can add parallel assembly station to eliminate bottleneck constraint. Next is to implement automated material handling to improve flow synchronization. And the last one is to cross-train all operators for flexibility and better resource utilization. So, as the conclusion, our project exceed product targets but reveal that success can mask serious inefficiencies. The key insight is theoretical calculation provides starting point, but simulation reveals operational reality. Computer-aided production management tools are essentially for optimizing modern manufacturing system. So that's all from us. Thank you very much.